So it turns out that our nearest star neighbor has an exoplanet. It's only about 4 light years away, so that means that it's actually potentially possible for us to get there and to explore it.
Using advanced space telescopes and probes, humanity has explored the mysteries of astrophysics and distant planets. One such planet, Proxima B, has been a fascinating subject of study as it orbits around the sun of their solar system, Proxima Centauri. Recently, the James Webb Space Telescope revealed the clearest image of Proxima B, offering amazing new insights that suggest a hopeful future for the possibility of human habitation. Join us as we reveal the most detailed image of Proxima B captured by the James Webb Telescope ever. Number 1. The James Webb Space Telescope's historical image of a nearby exoplanet. Proxima Centauri, discovered in 1915 by Scottish astronomer Robert Innes, is the closest known star to the Sun. In 2016, an international team of astronomers, led by Guillaume Anglada Escude, found Proxima B, an exoplanet orbiting Proxima Centauri within its habitable zone. This finding sparked enthusiasm due to its potential to offer insights into potentially habitable planets outside our solar system. Proxima B's significance goes beyond its celestial presence, as it offers an intriguing opportunity to explore the mysteries of distant worlds. This revelation was made possible through observations with the James Webb Space Telescope. The discovery of Proxima B marked a significant moment in astrophysics. Despite its proximity, technological limitations had previously hindered detailed exploration. However, recent breakthroughs, facilitated by advanced imaging and spectroscopic tools on the James Webb Space Telescope, have allowed astronomers to obtain the first direct image of this Earth-sized exoplanet. This image is groundbreaking, expanding our understanding of nearby celestial bodies and carrying profound implications for scientific exploration beyond our solar system. The JWST's capabilities have provided a pivotal achievement, offering a visual insight into an exoplanet located within the habitable zone of a nearby star. The breakthrough has sparked intrigue within the scientific community, reigniting the quest to comprehend the potential habitability of exoplanets and explore the prospects of life beyond our solar system. The James Webb Space Telescope was instrumental in this discovery by employing cutting-edge imaging and spectroscopic tools, enabling astronomers to directly capture an image of Proxima B. This capability has opened up new avenues for studying exoplanets and has revitalized scientific interest in exploring the possibilities of life beyond our solar system. The James Webb Space Telescope is positioned at the second Lagrange point, L2, which is approximately 1.5 million km or about 1 million miles away from Earth. This location is crucial for maintaining a stable orbit as the telescope revolves around the Sun. The JWST is a pinnacle achievement in our space age, equipped with advanced scientific instruments that can capture images and collect data across various wavelengths, especially in the infrared range. The telescope's primary mirror is composed of 18 hexagonal segments and has a diameter of 6.5 meters or 2,000.1 feet, making it significantly larger than its predecessors. To image exoplanets like Proxima B, the JWST utilizes its near-infrared camera and near-infrared spectrograph, among other instruments. The NIRCam is essential for imaging and detecting objects in the near-infrared spectrum, while the NIRSpec performs spectroscopy to analyze the chemical composition, temperature, and other properties of celestial bodies. Given Proxima B's distance from Earth and the challenges of observing exoplanets, the JWST's capabilities are essential. Its infrared sensitivity allows it to detect faint infrared light emitted by Proxima B, crucial for characterizing the planet, studying its atmosphere, and potentially identifying signs of habitability. The telescope's high resolution and sensitivity enable it to gather detailed information about exoplanets like Proxima B, significantly contributing to our understanding of these distant worlds. Like the James Webb Space Telescope, the Hubble Space Telescope, affectionately called HST or Hubble, has been observing the cosmos since it was launched into low Earth orbit in 1990. Although not the first of its kind, this space-based observatory is remarkable for its large size and incredible versatility. Beyond its scientific importance, the Hubble telescope has captured the public's imagination, becoming a symbol of celestial wonder in the field of astronomy. Named after the renowned astronomer Edwin Hubble, the telescope is a key part of NASA's prestigious Great Observatories program, an initiative that includes elite astronomical instruments aimed at unraveling the mysteries of the cosmos. The Space Telescope Science Institute plays a crucial role in this quest, tasked with selecting Hubble's celestial targets and meticulously processing the extensive data it gathers. Complementing their dedication, the Goddard Space Flight Center takes charge of the telescope's intricate operations. Together, these institutions contribute significantly to advancing our understanding of the universe. Number 2. Hubble's legacy and ongoing contributions to astronomical discovery. More than 30 years have passed since the Hubble Space Telescope embarked on its cosmic exploration, yet its profound impact continues to echo. Positioned in a low Earth orbit, it enjoys an unobstructed view of the universe, free from the atmospheric distortions of our planet. This unique vantage point empowers Hubble to delve into the deepest realms of space and time, capturing breathtaking images and offering invaluable insights into the origins and evolution of our celestial surroundings. A standout achievement of the telescope lies in its contribution to refining the measurement of the Hubble constant, a vital parameter for comprehending the rate at which the universe expands. Hubble's observations have yielded groundbreaking discoveries, bringing to light the existence of dark energy and dark matter, two mysterious components that wield significant influence over the cosmic landscape. The adaptability and longevity of Hubble are exemplified by its versatility. Through multiple servicing missions, astronauts armed with cutting-edge technology have performed intricate repairs and upgrades over the years. These missions not only extended the telescope's operational lifespan, but also bolstered its capabilities, enabling it to tackle an even wider array of astronomical phenomena. Hubble's ongoing journey through space stands as a testament to its enduring importance and ability to unravel the mysteries of the cosmos. The core of the Hubble Space Telescope houses an extraordinary 2.4-meter mirror, a technological marvel that serves as the portal to the cosmos. This expansive mirror, in conjunction with 5 primary instruments, operates across the ultraviolet, visible, and near-infrared segments of the electromagnetic spectrum. Positioned in low Earth orbit, Hubble avoids the atmospheric disturbances faced by ground-based telescopes, allowing it to capture high-resolution images with minimal background light interference. Hubble's prowess in visible light imaging has been pivotal in unraveling the mysteries of the universe, providing an unparalleled depth of vision into the cosmic expanse. The telescope's exceptional visual acuity enables it to record intricate details, generating some of the most detailed visible light images in the history of astronomy. These captivating visuals offer a profound glimpse into the celestial tapestry, showcasing the beauty and complexity of distant galaxies, nebulae, and other celestial phenomena. Beyond its stunning visuals, Hubble has played a crucial role in numerous breakthroughs in astrophysics. One of its landmark achievements is the precise determination of the rate of the universe's expansion, a fundamental parameter known as the Hubble constant. This revelation has significantly advanced our understanding of the cosmos and the dynamic processes governing its evolution. Hubble's contributions, extending far beyond its captivating images, underscore its indispensable role in expanding our comprehension of the vast cosmic landscape. The concept of space telescopes traces its roots back to as early as 1923. The Hubble Space Telescope, a realization of this visionary idea, emerged through collaborative efforts. Financed and built by NASA, the United States Space Agency, in the 1970s, the project also received significant contributions from the European Space Agency. Originally scheduled for launch in 1983, Hubble encountered challenges such as technical delays, budget constraints, and the tragic setback of the 1986 Challenger disaster. Hubble faced a pivotal obstacle during its launch in 1990, with an imperfection in its primary mirror causing spherical aberration and compromising its imaging capabilities. Despite this setback, Hubble's mission persevered. In a display of human ingenuity and determination, a servicing mission in 1993 successfully rectified the optics, restoring the telescope to its intended optical precision. The Hubble Space Telescope stands as a testament to human ingenuity and adaptability, being the only telescope explicitly designed for maintenance in the weightless expanse of space by skilled astronauts. Across 5 space shuttle missions, this celestial sentinel underwent a series of repairs, upgrades, and replacements, showcasing the resilience and versatility of both the telescope and the human spaceflight program. These daring repair missions not only extended Hubble's operational lifespan, but also ensured its state-of-the-art capabilities by addressing issues with all 5 of its main instruments. The 5th servicing mission of the Hubble Space Telescope encountered a major setback due to safety concerns, particularly heightened after the tragic Columbia disaster in 2003, which initially led to its cancellation.
The world was shocked after the brave crew on Space Shuttle Columbia was lost upon re-entry through Earth's atmosphere on its way home.
However, NASA Administrator Michael D. Griffin's approval reinstated the mission, ultimately achieving success in 2009. This mission highlights the steadfast commitment to the Hubble telescope's ongoing mission and the dedication of those working to keep it at the forefront of astronomical exploration. As of April 2020, Hubble marked its 30th year in operation, continuously pushing the boundaries of astronomical discovery. Impressively, its enduring legacy is anticipated to last until the 2030-2040 timeframe, showcasing the telescope's durability and the continual advancements in space technology supporting its mission. Within NASA's Great Observatories program, Hubble plays a crucial role as the primary visible light telescope. This specialization complements other observatories, covering different parts of the electromagnetic spectrum. For example, the Compton Gamma Ray Observatory focuses on gamma rays, the Chandra X-ray Observatory explores the X-ray spectrum, and the Spitzer Space Telescope investigates the infrared bands. Together, they offer a comprehensive understanding of the multifaceted nature of the universe. Number 3. Proxima B's orbital ballet captured by the James Webb Space Telescope. As Hubble continues its celestial journey, a new era in space observation emerged with the introduction of its successors. Launched on December 25, 2021, the JWST operates in the mid-infrared to visible band, promising to reveal previously unseen cosmic wonders with its advanced capabilities. Following in its footsteps, the Nancy Grace Roman Space Telescope is expected to launch in 2027, further expanding humanity's capacity to explore the mysteries of the universe. The decision to replace the Hubble Space Telescope with the James Webb Space Telescope was driven by the recognition of certain limitations inherent in the Hubble's technology and orbital location. Although groundbreaking in its time, the Hubble's instruments were rooted in 1970s and 1980s technology. Additionally, its placement in low Earth orbit did not completely shield it from atmospheric disturbances, impacting its observational capabilities. The need for a successor became apparent due to these limitations, leading to the development of the James Webb Space Telescope. The JWST was meticulously designed with larger and more advanced instruments, specifically optimized for infrared observations. This enhancement enabled the JWST to delve deeper into space, scrutinize the earliest galaxies, and characterize exoplanets in ways that the Hubble could not achieve. The JWST has provided us with unparalleled clarity in the fields of cosmology and exoplanetary studies, particularly in the case of Proxima B. The orbit of Proxima B around its parent star, Proxima Centauri, is a fascinating aspect of its characteristics. Despite its proximity to the red dwarf star, Proxima B is located within the habitable zone, a region where conditions may support the existence of liquid water. However, it's essential to note that Proxima B's location in the habitable zone differs from that of Earth. Proxima B receives a significantly distinct amount of energy compared to our planet, leading to notable variations in its climate, surface conditions, and overall habitability. Exploring the potential effects of this energy variance, such as extreme temperature fluctuations or unique atmospheric compositions, presents intriguing avenues for further research and understanding. Proxima B, despite being Earth-sized and potentially habitable, has remained elusive due to its distance of 4.2 light-years. Traditional telescopes, whether ground-based or in space, cannot directly photograph this distant world. The JWST, designed specifically for infrared observations, takes a different approach. Instead of visually capturing the planet, it focuses on specific infrared wavelengths, tracking the color changes of Proxima B as it orbits. This innovative method has opened up promising research avenues, and since the discovery of Proxima B in 2016, significant progress has been made in understanding this exoplanet. What sets Proxima B apart is its remarkably brief orbital period. The exoplanet completes a full revolution around Proxima Centauri in a mere 11.2 Earth days. This short orbital year raises intriguing questions about the environmental conditions and the potential habitability of the planet. The swift orbit of Proxima B implies that it is likely subjected to gravitational and tidal forces vastly different from what we observe and experience on Earth. These variations have the potential to significantly influence the geology, weather patterns, and the planet's ability to retain an atmosphere. Understanding these differences is crucial in unraveling the unique characteristics of Proxima B. While Proxima B's distinct orbital period presents a wealth of opportunities for scientific inquiry, there is still much that remains to be studied about this exoplanet. Ongoing research efforts are essential to further our understanding of Proxima B and the implications of its short orbital year on its overall environment and habitability. The initial identification of Proxima B resulted from employing the radial velocity method, a sophisticated technique for detecting exoplanets. This method involves observing subtle changes in a star's spectrum caused by the gravitational influence of an orbiting planet. To grasp this concept better, picture a star and its planets engaged in a cosmic dance. When a planet orbits a star, it not only revolves around it, but also exerts a gravitational pull, causing the star to wobble slightly as it moves together. Scientists on Earth can detect these minute changes in the star's light, indicative of the gravitational interaction with orbiting planets. In the case of Proxima Centauri, our observations of the emitted light revealed telltale signs pointing to the presence of the smaller Proxima B in orbit around it. This discovery marks a significant advancement in the exploration of exoplanets, prompting further investigations into Proxima B's atmospheric composition, surface features, and potential biological signatures. Understanding the intricacies of this neighboring exoplanet holds the promise of unlocking insights into broader questions related to habitability and the prevalence of life beyond our solar system. The identification of Proxima B and ongoing research into its characteristics contribute to pushing the boundaries of our understanding of distant celestial bodies and their potential to support life. The significance of this discovery is underscored by Proxima B's location within the habitable zone of its star, generating considerable enthusiasm within the scientific community. This rocky planet presents the tantalizing possibility of hosting conditions conducive to liquid water, a fundamental element for the emergence and sustainability of life as we understand it. Nevertheless, Proxima B faces notable challenges due to its proximity to its parent star, Proxima Centauri. The intense radiation emitted by the star poses a potential threat to the planet, capable of altering its chemical composition and impacting any potential biosphere. To comprehend the full extent of these effects, intricate models are necessary, considering the intricate interplay between radiation and the planetary environment. Number 4. JWST's clues to habitable environments and water dynamics. While Proxima B may have an atmosphere capable of sustaining liquid water, its proximity to the star may result in extreme weather patterns, including fierce solar winds and the potential for atmospheric stripping due to stellar activity. These conditions could give rise to an environment markedly different from Earth's, posing challenges for the flourishing of life. However, recent data from the James Webb Space Telescope indicates the presence of water vapors in Proxima B's atmosphere. This discovery is significant, as water is a crucial ingredient for habitability. Understanding the dynamics of water on this exoplanet is essential, as it could shed light on the potential for life in such an environment. While the challenging conditions make it less favorable for life as we know it, the mere presence of water vapors opens avenues for further exploration and underscores the complexities of habitability beyond our solar system. Contemporary scientific methodologies leverage advanced models and observational instruments, such as spectroscopy and atmospheric modeling, to remotely examine the atmosphere of Proxima B. Spectroscopic analysis, a key component of this approach, allows scientists to discern the composition of gases within the exoplanet's atmosphere. This, in turn, provides valuable insights into the potential existence of life-supporting elements like oxygen, methane, or carbon dioxide. The integration of spectroscopy with cutting-edge atmospheric modeling techniques not only enhances our understanding of Proxima B's atmospheric conditions, but also aids in formulating hypotheses regarding its habitability. Through these sophisticated tools, scientists can glean glimpses into the intricacies of the exoplanet's atmosphere, paving the way for a more nuanced comprehension of its potential to support life. Continued advancements in observational techniques and modeling are paramount for delving deeper into the mysteries surrounding Proxima B's capacity to host life. As technology progresses, these tools will play a pivotal role in unraveling the complexities of the exoplanet's environment and providing valuable insights into the broader question of habitability beyond our solar system. Despite the challenges posed by Proxima B's proximity to its star, entertaining the possibility of extraterrestrial life on the planet is certainly warranted. Earth itself provides real-world examples of life thriving in extreme conditions, known as extremophiles. These incredible microorganisms have demonstrated the adaptability of life to environments that were once considered inhospitable. On our own planet, extremophiles have been found in some of the most extreme locations, challenging preconceived notions of where life can exist. Examples include thermophiles, such as Thermus aquaticus, a bacterium thriving in hot springs, and Pyrobus fumari, found in deep-sea hydrothermal vents, where temperatures exceed 100 degrees C. Psychrophiles, on the other hand, flourish in freezing temperatures, as seen in Pyroa arcticus, which can survive in Arctic and Antarctic environments. Earth is also home to acidophiles like Acidobacillus ferrooxidans, thriving in highly acidic environments, while alkaliophiles such as Natronominus ferronis survive in highly alkaline conditions. Additionally, halophiles like Halobacterium salinarum live in highly saline environments, including salt flats, showcasing life's resilience to extreme salt concentrations. The existence of extremophiles on Earth suggests that environments previously deemed uninhabitable might indeed support life. In a similar vein, the extreme conditions on Proxima B could potentially be conducive to extremophiles, opening up new possibilities for the existence of life beyond our planet. The adaptability of life showcased by extremophiles on Earth underscores the potential for diverse forms of life in seemingly challenging environments, expanding our perspectives on the search for extraterrestrial life. Considering the challenging conditions on Proxima B, particularly the intense radiation stemming from its close proximity to the star, organisms similar to extremophiles on Earth may possess the capability to adapt and even thrive in such an environment. Earth's own extremophiles, such as Deinococcus radiodurans, exemplify the potential for life to endure extreme radiation levels, surviving doses thousands of times higher than what would be lethal to humans. Extremophiles have evolved a range of adaptation strategies, including DNA repair mechanisms, protective pigments, and unique cell structures. These adaptations suggest potential survival mechanisms that life forms on Proxima B might develop to withstand its harsh conditions. The discovery of extremophile-like organisms on Proxima B equipped to endure extreme radiation or other challenging environmental factors, could revolutionize our understanding of life's adaptability beyond Earth. Unveiling such organisms would not only redefine the boundaries of habitability, but also expand the realm of exobiology, indicating that life might persist in seemingly hostile extraterrestrial environments. However, acknowledging the potential for life on Proxima B is easier said than done. It requires meticulous research, advanced scientific exploration, and a thorough understanding of the intricate interplay between the exoplanet's conditions and the adaptability of potential life forms. Such a discovery would mark a significant leap forward in our quest to comprehend the potential for life beyond our home planet. Our relentless pursuit of knowledge encounters formidable technological hurdles when studying exoplanets like Proxima B. Despite challenges, humanity's commitment has propelled the deployment of sophisticated space telescopes and probes, revealing the mysterious dance of Proxima B within the gravitational embrace of Proxima Centauri. So how might overcoming these obstacles reshape our comprehension of distant celestial bodies like Proxima B? Number 5. Technological hurdles in studying exoplanets like Proxima B. Examining distant celestial bodies like Proxima B and other exoplanets presents formidable technological challenges. Currently, our ability to directly observe and analyze these remote entities is constrained. While telescopes like the James Webb Space Telescope provide valuable insights, they face limitations in capturing detailed images or conducting on-site analyses due to vast distances and technological constraints. Overcoming these challenges requires advancements in telescope design, sensor technology, and potentially revolutionary propulsion systems to facilitate interstellar missions. Future technologies dedicated to interstellar missions have the potential to transform our capability to explore and comprehend exoplanets like Proxima B. Innovative propulsion systems, such as solar sails, ion propulsion, and even theoretical concepts like warp drives, are currently under investigation. These technologies aim to significantly reduce travel time to distant star systems, enabling closer observations and potentially facilitating direct exploration of exoplanets. However, it is crucial to note that, at present, these concepts remain largely theoretical and demand extensive research and development before they can be deemed feasible for interstellar voyages. Exploring Proxima B holds immense significance in advancing our comprehension of exoplanets and the potential existence of life beyond Earth. The study of this exoplanet, along with others situated within its habitable zone, contributes vital data that refines our understanding of planetary formation, habitability conditions, and the prevalence of life-supporting environments in the cosmos. This knowledge plays a pivotal role in shaping the future of space exploration missions by guiding the selection of targets for further investigation and potential human colonization efforts. Proxima B, in this context, serves as a crucial stepping stone towards unraveling the mysteries of distant worlds, broadening the horizons of our understanding of the universe. The insights gained from studying Proxima B not only deepen our knowledge of individual exoplanets, but also have broader implications for the search for life and the potential habitability of celestial bodies beyond our solar system. The exploration of exoplanets extends beyond Proxima B, encompassing a diverse array of celestial bodies categorized into various classes. These classifications include gas giants like hot Jupiters, rocky planets resembling Earth or Mars, and unique entities such as super-Earths. Each class exhibits distinct features, offering the potential to support varied conditions for life. Significant discoveries within these categories have substantially broadened our understanding of planetary systems, revealing a vast spectrum of planetary diversity across the cosmos. Telescopes like Kepler and the James Webb Space Telescope have played instrumental roles in this exploration. Kepler, tasked with surveying a portion of the Milky Way, identified thousands of exoplanet candidates. The JWST, equipped with advanced capabilities, has furthered our insights by enabling the detection and analysis of exoplanet atmospheres, composition, and even the potential for habitability. Recent observations of Proxima B showcase the JWST's ability to shed light on these critical aspects. To grasp the importance of this discovery, it's crucial to understand the field related to Proxima Centauri. You see, Proxima Centauri is a small and lightweight star located about 4.2465 light-years away from our Sun, situated in the southern constellation of Centaurus. Its Latin name, meaning the closest star of Centaurus, highlights its remarkable proximity to our solar system. Discovered by Robert Innes in 1915, this neighboring star holds the distinction of being the closest known star to the Sun. Despite its remarkable status, Proxima Centauri remains elusive to the naked eye, boasting a quiescent apparent magnitude of 11.13. This faint luminosity places it beyond the reach of unaided observation, emphasizing the need for telescopic assistance to appreciate its celestial presence. Proxima Centauri holds membership in the Alpha Centauri star system, specifically designated as Component Alpha Centauri C, positioned 2.18 degrees southwest of the Alpha Centauri AB pair. Proxima Centauri currently resides 12,150 astronomical units, or 0.2 light-years away from its AB counterparts, engaging in a leisurely orbital dance with a period spanning approximately 550,000 years. In the cosmic hierarchy, Proxima Centauri earns the classification of a red dwarf star, boasting a mere 12.5% of the Sun's mass and an average density approximately 33 times that of our solar giant. Despite its modest size, the star's proximity allows astronomers to directly measure its angular diameter, revealing that it is about 1/7 the diameter of the Sun. Number 6. The enduring tale of Proxima Centauri's 4-trillion-year journey. Proxima Centauri, while typically characterized by a low average luminosity, exhibits a captivating flair for drama in its cosmic performance. As a flare star, it sporadically undergoes intense surges in brightness, driven by magnetic activity coursing through its stellar veins. The star's magnetic field, originating from convection processes throughout its celestial body, fuels these luminous outbursts, resulting in a total X-ray emission akin to our own Sun. As a celestial entity, Proxima Centauri's fate is intricately woven with the internal dynamics of its core. The convection-driven mixing of fuel within its stellar core, coupled with its comparatively modest energy production rate, charts a course that extends its main sequence existence for an astonishing 4 trillion years into the future. This longevity places Proxima Centauri on a cosmic stage as a stellar protagonist, showcasing the enduring dance of celestial bodies and the mysteries they hold within their fiery hearts. Proxima Centauri has introduced a group of planets that enhance its cosmic story. Among these celestial companions are Proxima Centauri B, Proxima Centauri D, and the somewhat controversial Proxima Centauri C. Leading the planetary trio is Proxima Centauri B, gracefully circling its stellar host at a distance of about 0.05 astronomical units, which is equivalent to 7.5 million kilometers. This exoplanet completes its elliptical orbit around Proxima Centauri in a quick 11.2 Earth days, possessing a mass of at least 1.07 times that of our planet. Importantly, Proxima Centauri B is situated within the habitable zone of its parent star, a region where temperatures might support the presence of liquid water on its surface. However, the red dwarf nature of Proxima Centauri, along with its tendency for stellar flares, has sparked heated debates among astronomers regarding the habitability of this exoplanet. In the vast expanse of celestial bodies, Proxima Centauri C emerges as a potential super-Earth, positioned at a more distant 1.5 astronomical units from its host star. This exoplanet leisurely completes one full orbit around Proxima Centauri every 1 to 900 days, equivalent to about 5.2 Earth years. In closer proximity, we find Proxima Centauri D, a sub-Earth entity, orbiting its stellar companion at a mere 0.029 astronomical units, finishing a swift orbit every 5.1 Earth days. Understanding Proxima Centauri's stellar characteristics requires recognizing its classification as a red dwarf. Belonging to the M5.5 spectral class, this red dwarf is firmly placed on the main sequence of the Hertzsprung-Russell diagram. Its M5.5 designation identifies it among the low-mass M-type dwarf stars, with a color subtly shifted toward the red-yellow spectrum due to an effective temperature around 3000 Kelvin. Proxima Centauri's faint luminosity is revealed with an absolute visual magnitude of 15.5, observable from a distance of 10 parsecs. Emitting a mere 0.16% of the Sun's total luminosity across all wavelengths, its visibility in the visible light spectrum, where the human eye is most sensitive, is further reduced to only 0.0056% of the Sun's radiance. Intriguingly, more than 85% of its radiated power resides within the infrared wavelengths, presenting astronomers with a distinctive signature for studying this mysterious red dwarf. A significant astronomical breakthrough occurred in 2002 when optical interferometry, employing the Very Large Telescope, unveiled the angular diameter of Proxima Centauri to be 1.02 plus or minus 0.08 milliarc seconds. Utilizing this data alongside the known distance to Proxima Centauri, astronomers calculated its actual diameter to be approximately 1/7 that of the Sun, or 1.5 times that of Jupiter. The star's mass, derived through stellar theory, is estimated at 12.2% of the solar mass, equivalent to 129 Jupiter masses. Although the mass has been directly computed from observations of microlensing events, it is done with slightly lower precision, resulting in a value of 0.150 solar masses plus 0.2062 solar masses minus 0.051 solar masses. Interestingly, Proxima Centauri's mass density deviates significantly from the standards set by the Sun. Lower mass main sequence stars, such as Proxima Centauri, demonstrate a higher mean density in comparison to their higher mass counterparts. Proxima Centauri is no exception, showcasing a mean density of 47 to 100 kilograms per cubic meter. In contrast, the Sun maintains a mean density of 1,411 kilograms per cubic meter. This divergence in density provides valuable insights into the distinctive characteristics of Proxima Centauri within the vast cosmic landscape. The gravitational influence exerted by Proxima Centauri is formidable, with a measured surface gravity expressed as the base 10 logarithm of acceleration in centimeter-gram-second units, reaching 520. To put this into perspective, Proxima Centauri's surface gravity is an astonishing 162 times greater than that experienced on Earth, emphasizing the extreme conditions prevalent on this relatively small, yet dense star. The rotational dynamics of Proxima Centauri have also captured the attention of astronomers. A 1998 study, tracking photometric variations, suggested a complete rotation cycle occurring approximately every 83.5 days. Subsequent investigations in 2002, utilizing a time series analysis of chromospheric indicators, hinted at a slightly longer rotation period of 116.6 plus or minus 0.7 days. The mystery deepened as later observations of Proxima Centauri's magnetic field revealed a rotation period of 89.8 plus or minus 4 days. This finding aligns with a measurement derived from radial velocity observations, yielding a period of 92.1 plus 4.2 minus 3.5 days. These nuanced insights into Proxima Centauri's rotational behavior add layers to our understanding of the dynamic processes governing this intriguing stellar entity. Number 7. The serene transition to a helium-white dwarf. Proxima Centauri's unique characteristics, attributed to its relatively low mass, result in distinctive features shaping its stellar structure and behavior. The star's interior is entirely convective, a consequence of its low mass, causing the transfer of energy to the exterior through the physical movement of plasma rather than relying on radiative processes. This convective nature gives rise to an intriguing phenomenon: the continual circulation of helium ash, remnants from the thermonuclear fusion of hydrogen, throughout the star's expanse. Unlike larger stars such as the Sun, which consume only about 10% of their total hydrogen supply before transitioning from the main sequence, Proxima Centauri is expected to use nearly all its fuel before hydrogen fusion concludes. The convective processes within Proxima Centauri play a pivotal role in generating and sustaining its magnetic field. This magnetic energy manifests at the surface through stellar flares, transient events that momentarily elevate the star's overall luminosity. On May 6, 2019, an exceptional flare event, classified between solar M and X flare classes, emerged as the brightest ever detected, marked by a far ultraviolet emission of 2 × 10 to the power of 30 ERG. This flare highlighted the dynamic and energetic nature of Proxima Centauri. These stellar flares, lasting as briefly as 10 seconds, contribute to the overall magnetic activity of the star. These magnetic flares are not just spectacular displays, they carry significant energy. Some of the largest flares can reach sizes comparable to the star itself, attaining temperatures as high as 27 million Kelvin, sufficient for the emission of X-rays. Proxima Centauri's quiescent X-ray luminosity, hovering around -12 multiplied by 10 to the power of 26 per second, is intriguingly similar to that of the much larger Sun. However, during the peak of the most substantial flares, the X-ray luminosity can escalate to an impressive 10 to the power of 28 per second. These magnetic flares not only offer a captivating display of stellar activity, but also provide invaluable insights into the intricate interplay of magnetic forces and convective processes occurring within Proxima Centauri. Proxima Centauri, though compact in size, unveils a stellar personality marked by dynamic and intriguing features, particularly evident in its active chromosphere and distinct spectral attributes. A noteworthy element in its spectrum is the prominent emission line of singly ionized magnesium at a wavelength of 280 nanometer, signaling heightened activity within its outer layers. Remarkably, around 88% of Proxima Centauri's surface is classified as active, a significantly higher percentage than the Sun experiences, even at the zenith of its solar cycle. This heightened activity extends beyond periodic flares, influencing the overall temperature of Proxima Centauri's corona. Even during quiet periods with minimal or no flares, the activity elevates the corona temperature to an impressive 3.5 million Kelvin, surpassing the Sun's corona temperature of 2 million Kelvin. Additionally, the total X-ray emission from Proxima Centauri, a crucial indicator of its activity, is comparable to that of the Sun. Notably, Proxima Centauri's overall activity level, although considered low when compared to other red dwarfs, aligns with its estimated age of 4.85 billion years. This consistency corresponds with the anticipated decrease in activity over billions of years as a red dwarf's stellar rotation rate diminishes. Further exploration into the star's behavior reveals a periodic variation in activity levels, with a roughly 442-day cycle, shorter than the solar cycle of 11 years. This periodicity suggests a nuanced interplay of internal processes and magnetic activity within Proxima Centauri, providing astronomers with a valuable glimpse into the star's intricate dynamics. Despite its active nature, Proxima Centauri exhibits a relatively weak stellar wind, amounting to no more than 20% of the mass loss rate of the solar wind. This peculiarity arises from the star's smaller size compared to the Sun. While Proxima Centauri's mass loss per unit surface area is 8 times greater than that from the solar surface, the overall stellar wind remains modest. This distinctive feature adds another layer to the multifaceted nature of Proxima Centauri, highlighting the nuanced balance between its size, activity, and stellar wind characteristics. A red dwarf with a mass similar to that of Proxima Centauri is expected to maintain its presence on the main sequence for an astonishing 4 trillion years. Throughout this prolonged period, the star undergoes a gradual transformation driven by hydrogen fusion, leading to an increase in the proportion of helium. Consequently, the star becomes smaller and hotter, eventually transitioning into what is referred to as a blue dwarf. In the concluding stages of this evolutionary phase, Proxima Centauri undergoes a significant surge in luminosity, achieving 2.5% of the Sun's luminosity. This heightened luminosity persists for several billion years, providing warmth to any celestial bodies orbiting around it. As the hydrogen fuel within Proxima Centauri becomes depleted, the star proceeds to evolve into a helium white dwarf, bypassing the red giant phase. During this subsequent phase, the star steadily loses any remaining heat energy, ultimately settling into a serene state as a helium white dwarf. Number 8. Proxima Centauri's gravitational influence on Alpha Centauri's planetary disks. The origin of the Alpha Centauri system, which includes Proxima Centauri, is theorized to involve a natural formation scenario. This intriguing hypothesis proposes that the system's formation resulted from the dynamic capture of a low-mass star by a more massive binary system within an embedded star cluster. However, the confirmation of this hypothesis awaits more precise measurements of the radial velocity. If indeed Proxima Centauri was bound to the Alpha Centauri system during its formative years, the stars in this cosmic trio likely share the same elemental composition. Proxima Centauri's gravitational influence on the Alpha Centauri. Protoplanetary disks may have stirred up these regions, potentially enhancing the delivery of volatiles, such as water, to the inner, drier regions. This possibility opens up the potential for enriching any terrestrial planets in the system with crucial materials, contributing to the intricate interplay of factors shaping the planetary dynamics within the Alpha Centauri system. An alternative scenario proposes that Proxima Centauri might have been captured at a later date during a cosmic encounter, resulting in a highly eccentric orbit. The eccentricity of this orbit would have been stabilized by the gravitational influence of the galactic tide and additional stellar encounters. This captivating narrative suggests that Proxima Centauri's planetary companions could have faced a lower risk of orbital disruption by the Alpha Centauri pair. As the Alpha Centauri duo continues to evolve, shedding mass over time, predictions indicate that Proxima Centauri may become unbound from the system approximately 3.5 billion years from the present. Following this, the star will gradually drift away from its stellar companions. In the realm of spatial measurements, Proxima Centauri, as of the Gaia Data Release 3 in 2020, is located at a distance of 4.2465 light-years from the Sun, with a parallax of 768.0665 plus or minus 0.0499 mass. This refined measurement builds on previously published parallaxes, such as Gaia DR2's 2018 measurement of 768.5 plus or minus 0.2 mass, the Research Consortium on Nearby Stars' 2014 measurement of 768.13 plus or minus 1.04 mass, the Hipparcos Catalog's 1997 measurement of 772.33 plus or minus 2.42 mass, the Hipparcos New Reductions 2007 measurement of 771.64 plus or minus 2.60 mass, and the Hubble Space Telescope's Fine Guidance Sensor's 1999 measurement of 768.77 plus or minus 0.37 mass. The combined data highlights the precision achieved in determining Proxima Centauri's position in our cosmic neighborhood. When observed from Earth, Proxima Centauri is situated 2.18 degrees away from Alpha Centauri, equivalent to 4 times the angular diameter of the full moon. Proxima Centauri displays a notable proper motion, covering 3.85 arcseconds per year across the celestial sphere, and has a radial velocity toward the Sun, measured at 22.2 km/second. If viewed from Proxima Centauri, the Sun would appear as a luminous 0.4 magnitude star in the constellation Cassiopeia, similar in apparent brightness to Achernar or Procyon when observed from Earth. Proxima Centauri holds a distinctive position among known stars, having been the closest star to the Sun for approximately 32,000 years, a proximity that will persist for about another 25,000 years. Following this period, a captivating celestial dance will unfold as Alpha Centauri A and Alpha Centauri B alternately claim the title of the nearest star to the Sun, switching approximately every 79.91 years. Scientific inquiries into Proxima Centauri's future trajectories have made predictions about its closest approach to the Sun. In 2001, J. Garcia Sanchez et al. Forecasted that Proxima Centauri would make its closest approach in roughly 26,700 years, approaching within a distance of 3.11 light-years. Subsequent studies, such as V.V. Bobilev's 2010 research, predicting a closest approach distance of 2.90 light-years in about 27,400 years, and C.A.L. Baylor-Jones's 2014 study estimating a perihelion approach of 3.07 light-years in approximately 26,110 years, have added a temporal dimension to our understanding of Proxima Centauri's dynamic relationship with the solar system. The focus shifts to Proxima Centauri, our nearest stellar neighbor. Recent observations from cutting-edge instruments have unveiled perplexing phenomena in Proxima Centauri's vicinity: dusty belts and mysterious flares. These celestial puzzles beg the question: what secrets lie within these dusty confines, and what triggers the cosmic flukes that captivate astronomers? Number 9. Unraveling the mystery of Proxima Centauri's dusty belts and flaring flukes. In its expansive voyage across the cosmos, Proxima Centauri is actively navigating the Milky Way, executing an orbital dance around the galactic center. The distance from the galactic center varies during its journey, oscillating between 27 and 31 light-years. This orbital path is distinctly characterized by an eccentricity of 0.07, indicating a mildly elliptical trajectory. These orbital parameters serve as crucial elements shedding light on the intricacies of Proxima Centauri's celestial journey within the vast galactic expanse. The slightly elliptical nature of its orbit adds a nuanced dimension to the narrative of Proxima Centauri's cosmic journey through the Milky Way. Proxima Centauri's connection to the Alpha Centauri binary star system traces back to its discovery in 1915, leading to occasional designations as Alpha Centauri C. This proposed companionship gained support from Hipparcos satellite data and ground-based observations, suggesting that Proxima Centauri, along with Alpha Centauri A and Alpha Centauri B, constitutes a gravitationally bound system. A pivotal confirmation of this gravitational link came in 2017 when Cervella et al. Presented high-precision radial velocity measurements, conclusively demonstrating the gravitational bond between Proxima and Alpha Centauri. The orbital dynamics unveiled an orbital period of approximately 547,000 years, characterized by an eccentricity of 0.5 plus or minus 0.08. Proxima Centauri's orbit takes it as close as 4,400 astronomical units during periastron and as far as 13,200 AU at apastron. Presently, Proxima Centauri is positioned at 12,147 plus or minus 260 AU from the Alpha Centauri AB barycenter, nearing the farthest point in its orbital journey. Expanding beyond the Alpha Centauri system, Proxima Centauri shares a common trajectory with 6 single stars, 2 binary star systems, and a triple star. Noteworthy co-moving stars include HD 4391, Norme, and Gliese 6676. The remarkable consistency in their space velocities, all within 10 kilometers of Alpha Centauri's peculiar motion, suggests the existence of a moving group of stars. This shared trajectory hints at a common origin, possibly within a star cluster or another stellar formation, revealing a shared cosmic journey connecting Proxima Centauri with its neighboring celestial companions. As of 2022, astronomers have made significant progress in exploring the Proxima Centauri system, unveiling 3 planets in its celestial vicinity. This discovery provides a glimpse into the diverse nature of exoplanetary systems surrounding our nearest stellar neighbor. The quest for exoplanets around Proxima Centauri began in the late 1970s and gained momentum in the 1990s. Multiple radial velocity measurements set constraints on the maximum detectable mass for a companion. However, the star's activity level introduced challenges, introducing noise to radial velocity measurements and complicating the detection of companions. A noteworthy development unfolded in 1998 when an examination utilizing the faint object spectrograph on the Hubble Space Telescope hinted at the potential presence of a companion orbiting Proxima Centauri at a distance of about 0.5 astronomical units. Subsequent attempts, employing the Wide-Field Planetary Camera 2, failed to confirm the existence of such companions. Astrometric measurements at the Cerro Tololo Inter-American Observatory also negated the likelihood of a Jupiter-sized planet with an orbital period ranging from 2 to 12 years. A significant turning point occurred in 2017 when a team of astronomers, armed with the powerful Atacama Large Millimeter Submillimeter Array, reported the detection of a cold dust belt encircling Proxima Centauri at a distance ranging from 1 to 4 AU. This belt, characterized by a cold temperature of approximately 40 Kelvin, boasts a total estimated mass equivalent to 1% of Earth. Intriguingly, researchers tentatively identified two additional features: a cold belt, maintaining a temperature of 10 K, positioned around 30 AU, and a compact emission source located about 1.2 arcseconds from the star. However, the initial intrigue surrounding these discoveries took an unexpected turn upon further analysis. The emissions associated with the cold dust belts and additional features were subsequently determined to be most likely the aftermath of a substantial flare emitted by Proxima Centauri in March 2017. Remarkably, it was found that the presence of dust within a 4 AU radius from the star was not necessary to model the observed phenomena, emphasizing the intricate nature of deciphering celestial mysteries. Proxima Centauri C, a potential super-Earth or gas dwarf, weighs around 7 times the mass of Earth and orbits at a distance of approximately 1.5 astronomical units, equivalent to 220 million kilometers. It completes one orbit around its host star every 1 in 900 days, approximately 5.2 years. To provide a comparative scale, if Proxima Centauri B were likened to Earth, Proxima Centauri C would share characteristics more akin to Neptune. The considerable distance of Proxima Centauri C from its host star renders it less likely to be habitable, given its low equilibrium temperature of around 39 Kelvin. Number 10. Life on Proxima Centauri B's hypothetical habitable zone. In April 2019, Italian astrophysicist Mario Damaso and his team brought Proxima Centauri C to our attention. Their discovery was rooted in subtle changes in radial velocity data from the European Southern Observatory's HARPS instrument, suggesting the potential presence of an additional planet orbiting Proxima Centauri. The planet's existence was confirmed in 2020, when Hubble astrometry data from around 1995 supported Damaso's initial findings. Efforts were made to directly image Proxima Centauri C, with the SPHERE detecting a potential counterpart in the infrared spectrum. However, caution is warranted, as a definitive detection remains elusive. If the observed source is indeed Proxima Centauri C, it exhibits an unusually bright appearance for a planet of its mass and age, prompting scientists to entertain the possibility of a ring system with an estimated radius of approximately 5 RJ. In 2022, a noteworthy study challenged the radial velocity confirmation of Proxima Centauri C. The findings from this study introduced uncertainty into the previously established evidence, prompting a re-evaluation of the planet's existence and characteristics. Scientific discourse and ongoing research contribute to a dynamic understanding of celestial bodies like Proxima Centauri C, underscoring the continuous evolution of our knowledge about the cosmos. In 2019, a team of astronomers embarked on a comprehensive reassessment of data obtained from Espresso to refine our understanding of Proxima Centauri B's mass. However, this meticulous review yielded an unexpected discovery. The researchers identified an additional radial velocity spike, displaying a consistent periodicity of 5.15 days. This intriguing finding suggested the possible presence of another planetary companion within the Proxima Centauri system. Upon closer examination, the astronomers estimated that if the newly detected signal indeed originated from a planetary body, it would possess a mass of no less than 0.29 times that of Earth. This discovery introduced a new layer of complexity to the Proxima Centauri system, hinting at the existence of an additional celestial body with a significant mass. To validate their findings, the team conducted further in-depth analyses. The confirmation of the signal's existence marked a pivotal moment in their research, leading to the formal announcement of this groundbreaking discovery in February 2022. The revelation of this potential planetary companion not only expanded our knowledge of the Proxima Centauri system, but also emphasized the importance of ongoing exploration and careful scrutiny of astronomical data. The disclosure of a potential planetary companion with a 5.15-day periodicity around Proxima Centauri enriches our understanding of the dynamics within this distant stellar system. As scientists delve into the intricacies of these celestial bodies, each discovery opens the door to new questions and avenues of exploration, highlighting the continuous evolution of our comprehension of the cosmos. In the TV documentary Alien Worlds, an intriguing story was told about the search for a potentially habitable planet around Proxima Centauri or other red dwarfs, specifically focusing on Proxima Centauri B. The documentary envisioned a planet within Proxima Centauri's habitable zone, located at a distance of 3.48.1 million kilometers from the star. This proximity could lead to tidal locking, where one side of the planet permanently faces the star. In the hypothetical scenario of a low orbital eccentricity, the planet's sky would exhibit minimal movement, resulting in perpetual day or night on most of the planet's surface. To address this, the presence of an atmosphere was considered crucial to distribute the star's energy. The relationship between the planet and its star depended on various factors, shaping the potential habitability conditions. One significant challenge discussed was Proxima Centauri's flare outbursts, which could potentially erode the atmosphere of a planet in its habitable zone. Despite this obstacle, Jabor Basri from the University of California, Berkeley, remained optimistic, suggesting that a strong magnetic field could act as a protective shield. Even a tidally locked planet, rotating once for every orbit around its star, could generate a protective magnetic field if part of its interior remained molten. However, the scientific community was divided on the feasibility of life around red dwarfs. Proponents of the rare Earth hypothesis expressed skepticism, arguing that tidal locking could result in a weak planetary magnetic moment, making the atmosphere vulnerable to erosion from coronal mass ejections. This debate added depth to the exploration of exoplanets and their potential for sustaining life. Number 11. A century of discovery and celestial surprises. In December 2020, the scientific discourse took an intriguing turn with the announcement of a candidate SETI radio signal, BLC-1, potentially originating from Proxima Centauri. Initial enthusiasm about extraterrestrial communication was later tempered when it was revealed that the signal was human-made radio interference. In the Chronicles of Astronomy, the pivotal year of 1915 witnessed a groundbreaking discovery by Scottish astronomer Robert Innes, who led the Union Observatory in Johannesburg, South Africa. Innes identified a star with the same proper motion as Alpha Centauri and proposed naming it Proxima Centauris. This proposal laid the groundwork for the star's nomenclature. 2 years later, in 1917, Dutch astronomer Joan Voete at the Royal Observatory at the Cape of Good Hope made a crucial contribution to understanding Proxima Centauri's position. Through meticulous trigonometric calculations, Voete determined the star's parallax to be 0.755 plus or minus 0.028, establishing that Proxima Centauri was at a distance from the Sun similar to that of Alpha Centauri. This revelation solidified the star's cosmic proximity and emphasized its significance as the lowest luminosity star in the astronomical realm during that era. In 1928, American astronomer Harold L. Alden delved further into Proxima Centauri's cosmic neighborhood. His precise parallax determination affirmed Innes's earlier assertion, locating the star at a mere 0.783 plus or minus 0.005 from the Sun. These collaborative efforts illuminated Proxima Centauri as a stellar neighbor, remarkably close to our solar system. Jumping ahead to 1951, American astronomer Harlow Shapley added another layer to Proxima Centauri's narrative. Shapley revealed that Proxima Centauri belonged to the category of flare stars, characterized by intermittent increases in brightness. Historical scrutiny of photographic records uncovered an 8% surge in magnitude, marking Proxima Centauri as the most dynamically active flare star of its time. Its proximity to Earth provided astronomers with an unparalleled vantage point to scrutinize and understand the intricacies of stellar flare activity. The evolution of astronomical observation technology thrust Proxima Centauri into the realm of X-ray scrutiny. In 1980, the Einstein Observatory created a detailed X-ray energy curve, unraveling the dynamics of a stellar flare on Proxima Centauri. Subsequent investigations, facilitated by satellites such as Exosat, ROSAT, and the Japanese ASCA satellite in 1995, delved into the X-ray emissions of smaller, solar-like flares from this intriguing celestial entity. Over time, Proxima Centauri has become a focal point for numerous X-ray observatories, including the likes of XMM Newton and Chandra, providing valuable insights into the cosmic choreography of this mysterious stellar neighbor. Proxima Centauri, positioned with a southern declination, offers its celestial spectacle exclusively to observers south of latitude 27° N. Despite belonging to the category of red dwarfs, Proxima Centauri, like others of its kind, eludes the naked eye due to its faint luminosity. Even from the perspective of Alpha Centauri A or B, Proxima Centauri appears as a fifth magnitude star. Its apparent visual magnitude of 11 mandates the use of a telescope with a minimum aperture of 8 centimeters for observation, particularly under optimal conditions. Clear, dark skies, with Proxima Centauri prominently placed above the horizon. In the realm of stellar nomenclature, a significant milestone occurred in 2016. Recognizing the necessity for standardized and cataloged star names, the International Astronomical Union convened a working group on star names. Their discussions resulted in the approval of the name Proxima Centauri on August 21, 2016. Consequently, this designation secured its place in the list of IAU-approved star names, affirming its status in the cosmic registry. Proxima Centauri, not content with mere subtlety, made a remarkable astronomical entrance in 2016 with the observation of a superflare, an extraordinary stellar outburst of unmatched intensity. This event propelled Proxima Centauri's optical brightness to an impressive factor of 68 pux, reaching approximately magnitude 6.8. The infrequency of such occurrences became apparent, with an estimated annual frequency of around 5 superflares, each lasting only a few minutes. The fleeting nature of these events had previously made them challenging to observe. In the year 2020, the New Horizons spacecraft captured a unique celestial rendezvous. During April 22 and 23, images of two nearby stars, Proxima Centauri and Wolf 359, were taken. A fascinating parallax effect, notably pronounced compared to Earth-based images, highlighted the spacecraft's distance from these stellar neighbors. Despite the visual spectacle, these observations, while illustrative, did not provide enhanced distance measurements beyond existing metrics. Number 12. The ethical implications of seeking extraterrestrial life. The observations conducted by the James Webb Space Telescope have revealed previously unseen details regarding the birth of stars and the formation of galaxies. This has significantly enhanced our understanding of cosmic phenomena. The JWST's expansive gaze has reached distant corners of the universe, unraveling mysteries that were once beyond our grasp. By peering through cosmic dust clouds and capturing faint glimmers of ancient light, This telescope has enabled scientists to study the formation of planetary systems, the composition of atmospheres and exoplanets, and the behavior of black holes in distant galaxies. The JWST, through its groundbreaking capabilities in high-resolution imaging and infrared sensitivity, is expected to revolutionize our comprehension of the early stages of the universe. It holds the potential to unveil the origins of galaxies and provide further insights into the conditions that led to the emergence of life. Anticipated contributions to future astronomical research are vast and promising. In terms of major advancements, we are now closer than ever to potentially making first contact with extraterrestrial life, especially if our speculations about Proxima B turn out to be true. This monumental event would reshape humanity's perspective on its place in the universe and transform various aspects of life on Earth. Confirming life beyond Earth would signify that life is not a unique phenomenon confined solely to our planet. It would redefine our understanding of life's existence, origins, and potential diversity in the universe. Furthermore, discovering life on Proxima B would catalyze advancements in scientific disciplines such as astrobiology, astronomy, and exoplanetary science. This could lead to unprecedented growth in these fields, fostering new discoveries and breakthroughs. However, making first contact would extend beyond scientific implications. It would provoke philosophical and existential contemplation about our place in the cosmos, prompting us to reconsider our values, ethics, and relationships with other life forms. This could stimulate a global dialogue on our responsibilities as inhabitants of a larger cosmic community. The exploration and attempt to communicate with extraterrestrial life have the potential to drive advancements in communication, linguistics, and technology. This quest could bring humanity together, transcending geopolitical boundaries in a collective scientific pursuit. The establishment of first contact might not only catalyze a shift in cultural narratives, but also inspire creativity in art, literature, and media. Furthermore, it may ignite a renewed interest in space exploration, motivating future generations to pursue careers in STEM fields. The discovery of extraterrestrial life has the power to foster a sense of global unity and cooperation as nations collaborate in deciphering and understanding this profound discovery. Such collaboration could extend to addressing global challenges, emphasizing our shared identity as inhabitants of the universe. However, these positive prospects raise ethical dilemmas regarding potential interactions with alien life forms and the impacts of our intrusion on them. Careful consideration of the consequences of our actions and the implications of contact on both civilizations is essential. Regardless, making contact with life on Proxima B would mark an unparalleled milestone in human history. This achievement would fundamentally alter our perspectives, aspirations, and understanding of life, propelling us into an era of unprecedented exploration and discovery. The exploration of realms beyond our world, despite persistent challenges, has yielded remarkable discoveries that have significantly altered our understanding of the cosmos. Advances in exoplanetary research, particularly recent revelations about Proxima B and its neighboring celestial bodies, have pushed the boundaries of our knowledge. The James Webb Space Telescope has played a pivotal role in this cosmic exploration, allowing humanity to witness the birth of stars, explore distant galaxies, and delve into the mysteries of exoplanets. The impact of the James Webb Space Telescope on cosmic exploration cannot be overstated. This groundbreaking tool has unveiled the secrets of the universe, unraveling the intricacies of Proxima B and peering into the depths of ancient galaxies. Its contributions have significantly advanced our understanding of celestial phenomena, leaving an indelible mark on the field of astronomy. In turn, it has served as inspiration for future generations of scientists. As we marvel at the vastness of the universe, it becomes clear that our pursuit of knowledge is an ongoing quest. The universe presents an endless tapestry of uncharted territories and unanswered questions, urging us to persist in our explorations and nurture our curiosity-driven scientific undertakings. With each new discovery and milestone, we are propelled further into the cosmic unknown. Our relentless pursuit of understanding the universe and our place within it continues to drive us forward in the face of the infinite possibilities that lie beyond. The James Webb Space Telescope, JWST, observed an extraordinary celestial event that surpassed imagination, a stunning cluster of lights emanating from a planet situated 7 trillion miles away. This astronomical discovery reverberated within the scientific community, prompting a re-evaluation of our fundamental understanding. Could these signals be messages from distant civilizations? Let's find out. Number 13. Unveiling alien lights. 7 trillion miles away with the JWST. The successful launch of the James Webb Space Telescope stands as a remarkable achievement for the United States National Space Agency, significantly advancing our understanding of the universe's nature, origins, and ultimate fate. Unlike its predecessor, the JWST is specifically designed to capture a wide range of light, spanning from long wavelength visible light to mid-infrared wavelengths. This capability offers a more expansive and clearer perspective of the cosmos. Recent groundbreaking findings by the JWST have captured the attention of both the scientific community and the general public. The telescope identified an extraordinary occurrence, a cluster of lights originating from a planet an astonishing 7 trillion miles away from Earth. Spectral analysis has led scientists to posit the possibility of extraterrestrial life on this distant celestial body, challenging traditional astronomical assumptions and sparking widespread curiosity regarding the existence of alien populations beyond our solar system. The significance of this discovery becomes apparent when we consider the staggering distance involved: 7 trillion miles, or approximately 1,040 light-years from Earth. This vast distance underscores the JWST's unparalleled ability to observe the universe from an unprecedented vantage point, pushing the boundaries of our observational capabilities and reshaping our comprehension of what lies beyond our immediate cosmic vicinity. However, this remarkable achievement is no accident. The JWST has been purposefully engineered to serve as a groundbreaking space observatory, surpassing the capabilities of its predecessor, the Hubble Space Telescope. Its meticulous design enables it to penetrate cosmic dust clouds and observe distant celestial objects with unprecedented clarity, unraveling hidden cosmic phenomena and providing unprecedented insights into the universe's origins and evolution. The JWST is equipped with a 6.5-meter diameter primary mirror, composed of 18 hexagonal mirror segments made of gold-plated beryllium. Its advanced infrared cameras, such as the near-infrared camera and the mid-infrared instrument, enable it to capture images and data across a broad spectrum of infrared wavelengths. These instruments empower scientists to study the intricate details of star formation, galaxy evolution, and planetary systems. To protect its sensitive instruments from the sun's heat and light, the JWST utilizes a sophisticated 5-layer sun shield made of high-tech materials like Kapton. This shield maintains the telescope's operating temperature at an incredibly low -266.75 degrees Celsius, a critical factor for its infrared observations. Situated at the L2 Lagrange point, approximately 1.5 million kilometers from Earth, the James Webb Space Telescope orbits the Sun instead of Earth. This strategic location provides a stable and unobstructed view of the cosmos, minimizing interference from Earth's atmospheric disturbances and heat. The JWST's unparalleled capabilities and cutting-edge instrumentation surpass previous observatories, ushering in a new era for humanity's exploration of the universe. A primary objective of the JWST is to investigate the atmospheres of exoplanets, searching for indicators of habitability and essential molecules like water and methane that may suggest the potential for life. As the telescope races to capture radiations from unimaginable distances, it also peers back in time to the earliest epochs of the universe. In this pursuit, the JWST captures light from the first galaxies, stars, and cosmic structures that formed billions of years ago, unraveling the mysteries of the universe's origins and evolution. Through meticulous observations of star-forming regions and galaxies, the JWST has significantly contributed to our understanding of the processes guiding the birth and evolution of stars, as well as the assembly of galaxies throughout cosmic history. The mission of the JWST extends far beyond our solar system, delving into the exploration and comprehension of the vast, diverse, and ever-expanding cosmic web surrounding us. The JWST has already uncovered numerous groundbreaking discoveries, reshaping our understanding of the cosmos. Before delving into its most shocking revelation, it's noteworthy that the telescope has recently captured detailed images of Stephan's Quintet, a group of 5 galaxies located approximately 290 million light-years from Earth. Among them, 4 galaxies engage in a cosmic dance, gravitationally interacting and colliding with each other, while one of these galaxies is closer to Earth, positioned about 40 million light-years away. The proximity of galaxies in this cluster provides scientists with a unique opportunity to observe their intricate gravitational interactions. These observations have unveiled galaxies in the process of merging, offering valuable insights into the dynamics of galaxy interactions, star formation, and the mysteries of dark matter that bind these galaxies together. Additionally, the telescope has captured a detailed image of the Carina Nebula, a star-forming region located approximately 7,600 light-years away. The images reveal a vast expanse of gas, dust, and stellar nurseries where new stars are born. This celestial region spans over 300 light-years and is home to a variety of stellar activities, giving rise to stars much larger than our Sun. Notably, Eta Carinae, a binary star system with eruptions in the 19th century, temporarily became one of the brightest stars in the sky. Number 14. JWST's Southern Ring Nebula Revelations. The Carina Nebula serves as a captivating celestial canvas that enhances our understanding of stellar birth, evolution, and the formation of planetary systems within stellar nurseries. The latest image from the JWST provides unprecedented clarity, allowing scientists to study the cosmic cliffs and structures within the nebula, furthering our understanding of star formation and nebular dynamics. Moreover, the JWST's observations of the Southern Ring Nebula, also known as the 8-burst nebula, have revealed a second star in the nebula's binary system. This discovery enhances our understanding of the nebula's composition and dynamics. Situated approximately 2,500 light-years away in the southern skies, the Southern Ring Nebula's distinctive figure 8 shape is formed by the expulsion of gas and dust from a dying star, captivating stargazers for centuries. At the center of the bluish haze within this nebula lies a dying star. Intriguingly, recent observations from the JWST have unveiled a previously obscured second star situated next to the prominent blue-hued star in the nebula. While astronomers were already aware of the nebula's binary nature, the newfound clarity provided by the JWST enriches our understanding of the nebula's structure and the dynamics within this stellar environment. Adding to the astronomical revelations, a recently surfaced deep field image showcases the galaxy cluster known as SMACS 0723. Positioned approximately 5 billion light-years away from Earth, SMACS 0723 is a striking assembly of galaxies within the Abell 773 galaxy cluster. It serves as a window to the early universe, revealing a cluster that existed during the cosmos's formative stages. The JWST's observation of SMACS 0723 presents astronomers with a unique opportunity to delve into the formation and evolution of galaxies in the universe's early history. The information gathered from this distant cluster aids in deciphering the intricate processes governing galaxy evolution, unraveling the cosmic narrative that has shaped the vast structures observed in the cosmos today. These discoveries underscore the transformative impact of the JWST on astronomy, pushing the boundaries of observational capabilities. The telescope provides invaluable insights into distant celestial objects, galaxy formation, exoplanet atmospheres, and the early universe, sparking intrigue within the scientific community. This paves the way for further exploration and discoveries with this extraordinary space observatory, hinting at the possibility of uncovering alien life and the potential for making first contact in the vast cosmic expanse. The James JWST has provided valuable data about WASP-96b, an exoplanet situated approximately 1,150 light-years away, equivalent to around 7 trillion miles. Despite its extreme temperatures, the analysis of this data has unveiled the presence of water vapors in the planet's atmosphere, suggesting the potential for alien life. The JWST's ability to detect infrared wavelengths has been crucial in making this groundbreaking discovery. Specifically, its near-infrared camera and mid-infrared instrument are highly sensitive to faint infrared signals. These instruments played a key role in conducting spectroscopic analysis, a technique that involves breaking down light into its constituent wavelengths. Exoplanetary spectroscopic analysis, like the one carried out on WASP-96b, involves studying the light emitted or absorbed by exoplanetary atmospheres. This approach provides scientists with essential information about the compositions, temperatures, and potential habitability of these distant worlds. The process relies on examining a planet's spectra, which is essentially the breakdown of its light into distinct wavelengths. This data is collected when a planet passes in front of its host star from Earth's perspective, a phenomenon known as transit. During transit, a portion of the star's light passes through the exoplanet's atmosphere, interacting with its chemical elements and molecules. As this light moves through the atmosphere, certain wavelengths are absorbed by specific chemical elements or molecules present in the exoplanet's atmosphere. These absorption features manifest as dark bands in the exoplanet's spectrum, indicating the wavelengths of light that have been absorbed. Scientists can analyze these absorption lines to deduce the elements or compounds present in the exoplanet's atmosphere. Each element or molecule leaves a unique fingerprint in the spectrum, enabling astronomers to identify and quantify their presence. This information not only helps in understanding the chemical composition of the exoplanet's atmosphere, but also contributes to determining its temperature profile and other atmospheric properties. In summary, the JWST's advanced capabilities in infrared detection, combined with sophisticated spectroscopic analysis, have allowed us to explore the atmospheric characteristics of distant exoplanets and assess their potential for hosting life. Number 15. Exploring the possibility of life on scorching exoplanet WASP-96b. Studying specific spectral features such as water vapor, methane, carbon dioxide, and other molecules provides valuable insights into temperature gradients, atmospheric compositions, and the potential habitability of celestial bodies. In the case of WASP-96b, the JWST employed prolonged exposure observations, collecting light over extended periods to detect and capture faint signals from distant sources. This method allowed the telescope to amass detailed photometric data, offering information on the intensity, wavelengths, and spectral characteristics of the mysterious alien planet. Considering the remarkable speed of light, which travels at approximately 186,182 miles per second, the observed lights by the JWST originated from an exceptionally remote location, underscoring the telescope's capability to explore distant regions of the cosmos with unprecedented precision. Now, delving into the specifics of WASP-96b, this exoplanet resides approximately 1,150 light-years away from Earth, within the constellation Phoenix. Initially discovered by the Wide-Angle Search for Planets project, WASP-96b is a gas giant with nearly half the mass of Jupiter. Its close proximity to its host star, WASP-96, positions it extremely near, completing an orbit in just 3.4 Earth days. To put it into perspective, 1 year on this alien planet lasts a mere 3.4 days. Crucially, spectrographic analysis of WASP-96b's atmosphere unveiled a composition conducive to life as we understand it. Of paramount significance is the detection of water vapor in the planet's atmosphere, a key indicator that enhances the potential habitability of this distant world. In summary, the detailed analysis carried out by the JWST has not only illuminated WASP-96b's intriguing characteristics, but has also expanded our understanding of exoplanetary atmospheres and their potential for hosting life as we know it. The identification of water vapor in the atmosphere of WASP-96b stands as a pivotal advancement in our comprehension of exoplanetary atmospheres. The methodologies applied to scrutinize the atmospheric conditions of this distant exoplanet establish a significant precedent for future observations, providing scientists with the tools to explore and characterize other alien worlds. Nevertheless, a notable challenge emerges when considering the potential habitability of WASP-96b. The planet's temperatures soar to around 530 degrees Celsius, a scorching environment that appears inhospitable for life as we know it. Despite this seemingly unfavorable condition, scientists remain undeterred and optimistic. Drawing inspiration from Earth's own extremophiles, organisms that thrive in extreme environmental conditions, researchers find hope for the possibility of life on WASP-96b. Earth's extremophiles have been discovered in some of the most hostile environments, including the depths of ocean hydrothermal vents, acidic hot springs, and even within the icy expanses of Antarctica. These extremophiles defy conventional notions of habitability and have expanded our understanding of where life can thrive. The resilience of these organisms prompts scientists to consider the possibility of similar extremophiles existing on distant exoplanets like WASP-96b. Drawing parallels with the extremophiles found in Earth's deep-sea hydrothermal vents, where unique microbial life flourishes despite immense pressure and extreme temperatures, provides a framework for contemplating life in seemingly harsh extraterrestrial environments. The organisms in deep-sea hydrothermal vents have adapted to challenging conditions, relying on chemosynthesis instead of photosynthesis for energy production. This adaptation involves deriving energy from chemical reactions rather than sunlight, showcasing the potential for life to thrive in unconventional ways. Despite the scorching surface conditions of WASP-96b, rendering it inhospitable for life. As we currently understand it, the recent discovery of water vapor in its atmosphere has sparked intriguing possibilities. Scientists are now contemplating the potential existence of extremophiles or microbial life that might endure or inhabit the upper layers of the planet's atmosphere. Much like Earth's extremophiles challenged preconceived notions about where life can thrive, the identification of water vapor on distant exoplanets invites speculation about life's adaptability in seemingly hostile environments. The spectrographic analysis of WASP-96b's atmosphere has revealed the potential for life on a planet that, at first glance, appears almost infinitely distant and unwelcoming. This groundbreaking discovery urges a re-evaluation of our understanding of exoplanetary atmospheres. Spectroscopy, a technique used by scientists to study the specific wavelengths absorbed or emitted by elements or molecules, has rarely yielded results as surprising as those seen in the case of WASP-96b. The detection of water vapor, despite the planet's extreme temperatures, challenges traditional assumptions about habitability and raises questions about the potential resilience of life in unexpected places. Moving forward, Further exploration of WASP-96b's atmospheric dynamics is imperative. Scientists need to delve deeper into understanding the mechanisms behind the presence of water vapor and its distribution within the planet's atmosphere. This includes investigating the atmospheric structure, temperature gradients, and potential weather patterns. Such in-depth analysis is crucial for unraveling the evolutionary processes at play on this distant gas giant. Number 16. Revolutionizing exoplanetary research. The revelation of water vapor in the atmosphere of an exoplanet, even in the face of extreme conditions, has prompted scientists to ponder its implications. While the scorching temperatures on the surface of WASP-96b make it inhospitable, the data has sparked speculative discussions about the potential existence of habitable zones or layers within its atmosphere. Scientists are now contemplating hypothetical scenarios where life, perhaps in the form of extremophiles or possessing unique adaptations, could potentially survive or thrive in more temperate or shielded atmospheric layers. This novel perspective challenges traditional notions of habitability and broadens our understanding of where life might persist in the universe. The interpretation of data from WASP-96b extends beyond the immediate discovery, having profound implications for exoplanetary research. It establishes a precedent for analyzing exoplanetary atmospheres and refining techniques for detecting molecules in extreme environments. This methodological advancement opens new avenues for studying a diverse array of exoplanets, expanding our understanding of their atmospheric compositions. The intrigue among scientists generated by this discovery catalyzes further exploration and observation of exoplanets sharing similar characteristics. The analysis of WASP-96b's atmosphere not only deepens our knowledge of this specific exoplanet, but also acts as a stepping stone for future studies aimed at unraveling the diversity and potential habitability of exoplanetary atmospheres beyond our solar system. The recent revelations from the James Webb Space Telescope represent a monumental leap in humanity's understanding of the cosmos. These groundbreaking discoveries reshape our perception of the universe, providing captivating glimpses into the mysterious worlds beyond and sparking profound questions about cosmic diversity and the potential for life. These revelations fundamentally alter our cosmic perspective, highlighting the expansive diversity and mysteries that exist within the universe. They provoke contemplation about our place in a cosmos filled with awe-inspiring phenomena and potential habitats for life. This shift in understanding fuels curiosity, propelling us to seek deeper insights into the vast and intricate cosmos. The findings from the JWST propel us into an era of unprecedented exploration, breathing new life into our pursuit of unraveling distant cosmic mystery. They stimulate advancements in astronomy and astrophysics, fostering innovative methodologies to uncover the secrets concealed in the depths of space. These discoveries act as catalysts, driving the development of state-of-the-art technologies and missions dedicated to unraveling the unknown. In light of these remarkable discoveries, there is an urgent call for expanded exploration and comprehension of celestial wonders. They underscore the imperative need for continued investment in space exploration, fostering technological advancements and collaborative interdisciplinary studies. These discoveries inspire scientists, researchers, and space agencies worldwide to delve deeper, pushing the boundaries of our cosmic knowledge. Ultimately, the revelations of distant celestial phenomena by the JWST urge humanity toward a profound expedition, fueled by curiosity and a thirst for understanding. They guide our journey to decipher the universe's intricacies, providing unparalleled insights into the vastness and diversity of cosmic existence.